Welcome, everyone. And we're happy to have you join us for the first session of our virtual workshop on health applications for satellite-derived air quality. This session is on setting the stage for trusted high-quality satellite remote sensing data of air quality and health applications. And I'm Allison Patton. I'm a senior scientist at HEI. Now, before we begin, there are a few housekeeping details. All attendees are muted and view only for the duration of the webinar. There will be a Q&A period after the presentations. Please submit questions via the Q&A function at any time during the webinar. You can also upvote questions in the Q&A box. If you experience any logistical difficulties, please contact us using the chat box. Webinar slides and video will be available in the coming weeks. Please check the HEI website for details at the link shown on the slide. We also would like to hear about your work on satellites, air quality, and health. We've prepared a pre-workshop survey available at the link at the slide, and that link will also be posted in the chat. Today we have attendees from all around the world and many different fields. So I'll tell you a little bit about HEI. We're an independent nonprofit corporation chartered to provide policy relevant, high quality, and impartial science. We're funded jointly by government and the worldwide motor vehicle industry and occasionally private foundations. We fund research that is selected, conducted, overseen, and reviewed independently of HEI sponsors. Additionally, we have independent committees that select and oversee the studies, and then a different committee that reviews the studies before reports are published. We publish all of the results, whether they're positive or negative, and we also do not take policy positions. The workshop today is part of the work of HEI's research committee. The research committee and staff work together on strategic planning, defining research needs and requests for applications, and selecting and overseeing funded studies. The chairs of this workshop are Dr. Jeff Brook, who will soon be kicking off the scientific content, and Dr. Heather Holmes, who you will see in later sessions. So this is the first of 4 webinars. We hope that you'll be able to join all 4. So we're starting by setting the stage. Next week, we'll hear about global applications of satellite-derived air quality data. Then we'll look at how the methodological limits are being pushed in various ways. And we'll end with the roundtable discussion on the future of satellite remote sensing of air quality and health applications. Today's session has 3 talks on satellite remote sensing of air quality, and specific application and capacity development. Each talk will be about 20 minutes, allowing a little time for brief clarifying questions between talks, or we can discuss more thematic questions during the Q&A at the end. And now we have a distinguished set of speakers. This session will be chaired by Dr. Jeff Brook and Dr. Tracey Holloway. And so now I'll hand the mic over to Jeff to introduce the rationale for this workshop.
Okay, great, Allison. It's really a pleasure to be here today, and I really I'm appreciative of HEI for organizing and hosting this important workshop. Now, when I first saw the images produced by Gomes, Skiamaki, and Modis a little over 20 years ago, it was really eye-opening. Having been constrained to really essentially just touches of the elephant, and that was provided by sparse surface mire networks, and maybe a bit about what models predicted. We could see that those first pictures were really worth at least 1,000 words. affirming and refining what mental models we had at that time. We could see footprints of cities, the haze accumulating in parts of the San Joaquin Valley, and atmospheric transport patterns from local to hemispheric scale. Personally, I gained a new appreciation for what decades, if not a century of physics, engineering, and model development had enabled. And I can only imagine that Einstein had a role in it one way or another. Data assimilation for modeling got a boost. It became possible to assess trends and conduct accountability studies related to emissions. And we gained new insights on a range of geophysical processes, from lightning NOx production to bromine chemistry in the Arctic. Now, much more complete spatial patterns of population exposures and useful for population exposure estimates were not far behind in this progress that we experienced. I just want to share a few slides with you. Try anyways to put these up as I continue to open this presentation. Where is it? There we go. So, as I said, there was much progress over the years that this started to become more and more possible to use in air quality and health research, and much more complete spatial patterns useful for population exposure assessment were not far behind. In this, if you can see the slide, we can see here a reminder of the Canadian Census Health and Environment Cohort. And satellite observations literally made this possible and helped reveal association between PM2.5 and mortality at low ambient concentrations. Now we have concentration response functions for global air pollution burden estimates that are increasingly based upon consistent data and possibly able to inform us of the nature of the relationship, such as the extent of linearity and the existence of thresholds at the population level. And here we can see, some of the impact here in terms of the global coverage of PM2.5 and the satellites, and the estimates of mortality associated with air pollution in the more recent global burden disease estimate. And without maps like this from satellites, these estimates really would not be possible or not be as complete or as consistent as they are today. I think it's also important to consider the role satellite measurements play in pollutants beyond PM2.5 and ozone, such as we can see here for a range of trace gases. And while there is much progress in bringing in satellite information for ozone, this image here is from just a combination of model and surface measurements, and more work needs to be done in that area. And so I had to strike out ozone from that map. So where are we now in applying satellite-based air quality products to learn about air pollution and health effects? Well, today's webinar, as well as 3 subsequent webinars with a panel discussion, will give us an opportunity to consider these questions and more. And I think really we have a unique opportunity to think about a cross-disciplinary exchange amongst groups that hopefully this series of webinars will facilitate. For some of the presentations, including those from Yang Liu and Qian Dai, we'll see that today, in terms of state-of-the-art air pollution exposure assessment, finer resolution surface concentration maps of ambient exposure are increasingly available for many parts of the world. And satellite data, while valuable for this, are just one of multiple inputs to complex empirical data fusion models, including some that offer daily exposure estimates across large populations. These models are helping us to harness more and more health data sets for epidemiological studies and an increasing number of outcomes, including for certain subpopulations and for an increasing number of countries. The value of satellite observations for tracking wildfires and protecting the populations at risk is really unquestionable and an essential service for public health with our changing climate. Clearly, also, many more studies are inevitable and knowledge will surely increase on many fronts, thanks to the recent renaissance in satellite products. But where and how will it advance us in regards to some fundamental questions that remain? There are some questions we need to keep in mind. And I put them up here now for you to think about now and throughout this workshop. These are very, very broad questions. But coming back to the more fundamental questions, we do have to think critically about what role satellite observations, including tropomi, and the geostationary satellites like GEMS, TEMPO, Sentinel, and GO-16, as well as Maya, can play in resolving them, these fundamental questions. Air pollution health research has advanced tremendously over the past 25 years, and while satellite data has had an impact, the key questions, those of most relevance to policy, have become increasingly specific, just like in the satellite community. Many of these questions are captured in HEI's strategic plan, which covers 4 general categories. Can the health benefits of past air quality improvements, both short and long term, be unequivocally detected and quantified? This is the accountability issue. Also, over the past 25 years, we've returned time and time again to the questions of whether future policies can or should target PM components, or maybe sources, or certain PM sizes, including ultrafines, not to mention how to assess the relative roles and interactions amongst particles and gaseous co-pollutants. We know that we inhale complex mixtures. Also, keeping on top of current impacts of transportation emissions and future impacts from new developments in transportation, industry, and energy really often requires focus on the urban scale or smaller, even smaller, while global health clearly could imply very large scales. So we need to keep in mind the types of studies that have most promise for addressing these challenges and how satellite data can help. Back to no slides here now. I would say that observations from satellites have much potential, but what could their ongoing place be in health research, and what are the greatest opportunities? Those are things I hope that come out in these series of webinars that we have now going. So now I'd like to introduce the co-chair for today's session, Tracey Holloway. She is a professor in the Nelson Institute for Environmental Studies and the Department of Atmospheric and Oceanic Sciences at the University of Wisconsin-Madison. Tracey is a team lead for NASA's Health and Air Quality Applied Sciences program. And as you can see in her bio, she has a broad range of research and teaching interests. So Tracey, I turn it over to you now to lead us through the start of the session. Thank you.
Thank you, Jeff. And thanks for that really thoughtful overview. It's really exciting to hear HEI's perspective on the past, current, and future opportunities to connect Earth observations with health studies. And this term Earth observations, this is really the terminology that's used by NASA and other space agencies that are leading the way with satellite data relevant for air pollution exposure. For many of us who do most of our work here on Earth, the idea of Earth observation seems obvious. Every observation is Earth. But from NASA's perspective, observing Earth is one part of their portfolio. But it's a part of their portfolio that's especially exciting for social applications. And in fact, there's a division of NASA called the Applied Sciences Program that is very active in trying to bridge health users, air quality interests, and other environmental and decision-making issues with this network of space-based tools that can observe the Earth. So it's been exciting for me to be involved in these efforts since they began in 2011 with the NASA Air Quality Applied Sciences team. And that team went for 5 years. And then when it was recompeted in 2016, there was really an understanding that health needed to be front and center of these discussions. So the team was renamed the Health and Air Quality Applied Science Team, which has a funny acronym that we pronounce HAQAST. And we've been working now for about 10 years. And I've been the director of HAQAST for the first and now ongoing second iteration. And it's been a real pleasure to be working with researchers from across the US and around the world to answer some of the same questions and pose some of the same questions that this HEI session and this whole month of sessions will be taking much further and looking at from a health lens. So there's really no one better to kick off today's session than my colleague Yang Liu, who is a professor at the Rollins School of Public Health at Emory University. Yang has been part of the NASA Applied Sciences teams on health and air quality since they began in 2011. And his work not only applies satellite data to health, but is really developing the data products that are well suited to these new health relevant applications. So Yang, look forward to your talk.
Thanks, Tracey, and good day, everyone. It's a great pleasure to share some of my experiences and knowledge over many years working in this space. And I also want to thank HEI for giving me this opportunity to kick off our first session. Let me start sharing my screen. Okay, so I changed the title slightly so that we can see satellite remote sensing through the lens of air quality and health, given the interest of the HEI and its audience. So let me just start right off the bat from the key takeaways. So there are 3 points I want to drive through my presentation. The first one, like Jeff and Tracey said, satellite remote sensing offers many unique advantages as compared to other technological platforms for air quality monitoring, and it can be a very powerful tool. But it's still relatively new to air quality and health communities. We're aware that satellites offer comprehensive spatial coverage. Its time series of observations are growing. There's an increasing set of parameters available. The accuracy and resolution are also improving. And more fundamentally, satellite remote sensing through the electromagnetic spectrum offers non-intrusive measurements, and it's less prone to human error. These are some of the major advantages of this technology. And there has been an increasing number of successful applications in the space of air quality and health. And more exciting satellite capabilities are to come in the coming years. And then the last point I want to make through my presentation is that resources are there to get you started and also provide technical support. HAQAST being one of the major resources. My talk includes 5 parts. I'll provide a very brief overview of satellite remote sensing technology, and then say a little bit about how to access satellite data products, and make a distinction between satellite data products and air quality data products. I'll provide a few examples of how satellite data have been applied in health effects research and air quality monitoring. And then I'll talk a little bit about the major emerging capabilities in satellite missions. And finally, I would like to offer my sort of food for thoughts in terms of the upcoming challenges and opportunities in this space. Okay, to get everybody on the same page, the first question many people may ask, what do satellite measure exactly? Well, satellite measures scattered UV, visible, near infrared light, and sometimes it also collects emitted thermal infrared radiation. And when the the incoming solar radiation undergoes multiple processes when it enters the atmosphere, as indicated in this diagram that I borrowed from a very helpful resource that is NASA's Applied Remote Sensing Training Program, or RSAT. So the incoming solar radiation can be absorbed by trace gas species at certain wavelengths. It can be absorbed and bounced back by clouds or aerosols in the atmosphere. It can interact with the aerosols in the atmosphere, be scattered, be absorbed, be turned into other radiations. The remaining sunlight, for example, after passing the atmosphere, will also interact with the Earth's surface. It can be absorbed by the surface, as the surface is relatively dark. It can be reflected by the Earth's surface. Now, the Earth's surface is not a complete black body. It emits infrared radiation back to space. And that part of the atmospheric pathway can also interact with the atmosphere before the Earth leaving radiation is detected by the satellite instruments. Most of the time, the satellite instruments or instruments aboard the International Space Station fly way above the atmosphere. The lowest orbit is above 100 kilometers above the ground. And the most common satellite sensors flying in the sun synchronous orbit has a 650 to 850 kilometer altitude. So that's why the received electromagnetic radiation at different wavelengths carried information through the interaction between sunlight and different media, such as the atmospheric components and the land surface itself. So the so-called satellite retrieval of aerosol and trace gases is basically trying to reverse engineer this whole process and say, okay, given the measured intensity of reflected or emitted solar radiation, how do we estimate the composition and properties of these objects that the sunlight actually interacts with? Okay, so a retrieval algorithm is essentially a model that works to infer the physical quantities of these objects, be it aerosols, gas molecules, land surface, and so on. They're trying to infer the physical quantities such as number density, partial pressure, column amount, vertical profile, based on the spectral signature for each atmospheric constituents. Therefore, the fundamental assumption here is that for something to be detectable by a satellite instrument, it must present a unique spectrum signature, meaning a combination of wavelengths would be able to determine either the abundance or the feature of, say, a trace gas or aerosols in the atmosphere. Large-scale quantitative environmental remote sensing of the Earth really started in late 1990 with the launch of NASA's Terra satellite. Before that, there are other instruments that have that capability. It's just the remote sensing community had started to dedicate a huge amount of attention and effort in creating a lot of satellite products for users outside the remote sensing community, starting in early 2000. So far, we're able to get quite an impressive set of parameters as shown in this slide. In terms of aerosols, satellites are now able to offer aerosol optical depth, or AOD. Sometimes it's called aerosol optical thickness, or AOT. Phi-mode fraction, absorbing aerosol optical depth, particle size and shape indicators, smoke mask, and vertical profile retrieved from LiDAR-based instruments. Now, the vertical profiles, the LiDAR-based vertical profiles are sparse in coverage by the nature of the detection technology. And in terms of trace gases, satellites are able to offer NO2, SO2, CO, methane, ammonia, formaldehyde, and CO2 abundances estimates. And also to a lesser sense or lesser accuracy ozone. The current ozone detection technology has less sensitivity in the planetary boundary layer. Tropomi and later TEMPO would hold the promise to bring us down to the surface so that the satellite-based ozone product can have air quality and health applications. Okay. And if this is very exciting and you want to know more, I recommend that you visit the NASA HAQAST team website led by Tracey Holloway, and this is kind of the primary NASA's effort to make the connection between NASA data and tools with health and air quality stakeholders. And actually, that is the core mission of HAQAST. And its URL is very simple, it's haqast.org. So on this website, you will find data, you will find tools, and more importantly, you will find people. The HAQAST PIs and all the affiliated research teams who can work with you to actually solve your problems, not just our scientific endeavors. And this website also offers answers to questions asked by many early stage users. For example, why do we want to use satellite data? What can I do with it? And how do I get started? Okay, all of these questions have been thought over many times by the HAQAST team and their stakeholders, and the answers are summarized on the HAQAST website. Now, if you have done all that homework and you're ready to go actually explore the world of NASA data, NASA actually offers a one-stop shop portal called Earth Data. This is just a screenshot of his interface. At this portal, you will be able to find anything, everything NASA has ever produced for the public. Okay, however, a caution, if you have never heard of HDF or NetCDF file formats, I suggest you don't touch that NASA Earth Data portal. Instead, visit another website called the RSAT. RSAT is the dedicated capacity building program managed by the NASA Applied Science program, and it offers many from entry level to advanced training materials that are accessible to many non-remote sensing experts. So this is a highly recommended resource. And here, I really want to make this distinction that satellite data does not equal air pollution concentration. Okay, because most satellite parameters are column integrated measures, and most of them are optical measures. Even if we assume that the total column is strongly correlated with the pollutants in the boundary layer near the ground, as this assumption is true in many cases, models still need to be developed to convert satellite parameters to ground level air pollution mass concentrations for air quality and health applications in most cases. So there are kind of rules of thumb or general game plans if you want to explore a quantitative air pollution exposure assessment with satellite data as its primary driver. And the overall strategy goes like this. So first of all, you identified the satellite parameters that are strongly or potentially correlated with a particular air pollutant. And ideally, in advanced applications, you need to come up with a way to perform gap filling because of the data missingness caused by cloud cover. Very often, gap filling is done by chemical transfer model simulations fusing with existing satellite data, or imputation or other statistical ways of interpolation and extrapolation. So once you have a data layer, so to speak, of the satellite parameters that you're interested in, you also want to include meteorology, maybe land use as covariates to improve and stabilize the performance of your model. Because like I said, satellite measures the total column, and that relationship between the total column and the boundary layer is very often modified by weather and land use. Okay, so these are important parameters to include in your overall estimation model. And of course, this model is anchored on ground truth. So that's where the translation or conversion comes in. And we want to use ground truth for model training. And once the model is trained for your particular study domain, you can use it to generate pollution maps as the model predicts pollution where there is satellite data, but not ground truth. And my experience in this space so far is the maturity of this type of strategy is the best for PM 2.5. There are more studies now for nitrogen dioxide and other trace gases such as ozone and SO2. The methodology is less mature. Okay. So for just to give you an example, if we want to build a PM 2.5 model, what you need is satellite data such as the aerosol optical depth. Very often you want to use a normalized difference vegetation index. You want to have about elevation data. In my own applications, I would introduce either weather station data or gridded reanalysis, meteorology, and land use, land cover, population, road network, so on and so forth. And this model will be able to generate continuous PM maps in space and time. Nowadays, for PM 2.5 modeling, the spatial resolution can be as high as 1 kilometer. The temporal resolution is approaching hourly level. Okay, and PM models are often have very good accuracy and has been extensively used in both acute and chronic health effects research. Now, a caveat here, model performance depends heavily on the quantity, quality, and distribution of ground PM measurements. In terms of model formats, there are many different formats. If you like statistical models for their transparency and hypothesis testing capabilities, you have many choices like multivariate regression, mixed effect models, generalized entity models, GWR, or some combinations of these structures. And in recent years, machine learning is gaining popularity in this space. There are many studies using random forest, gradient boosting, neural network, or deep learning approaches. And the maps showing here are the end products of these studies. I'm showing PM concentrations, NO2 concentration maps, and very recently my own group's work on high resolution ozone, ground level ozone concentration mapping. And there are no textbooks in this space. It speaks to the kind of the youth of this interdisciplinary field. But there are in-depth literature reviews that offer insights to help you develop your own capabilities. And some of the reviews are actually contributions from various cycles of the HAQAST team. And in terms of applications, we have seen quite a few high-profile studies in recent years, right? So on the left-hand side, you see the global burden of disease, dedicated study to the ambient air pollution disease burden, and then PM 2.5 and ozone have been included in the overall global burden estimations together with dozens of other risk factors. And regionally, we have seen NO2 mortality studies, PM and infant mortality studies, PM and Medicare and elderly health, elderly mortality in the US, and also in China. There's a recent paper on ambient PM and the incidence of stroke. So a lot of large-scale studies have been driven by satellite-based exposure estimates. And about 3 years ago, a group of experts wrote a workshop summary report that shows this map. And you can see on this diagram, satellite monitoring is best suited for daily to annual temporal scales, and also city to global spatial scales. If you go down to real time, or you go down to street or neighborhood level, satellite data is still developing. It does not have a robust track record. And even for experienced users, developing a custom-made satellite-based air quality data set can be time-consuming. So before you decide to take a deep dive, I recommend you to check out existing data set. I mean, I call it off-the-shelf data sets, to just get an idea of what satellite-based air quality data feels like for you. And the methodologies used to generate these data sets are all published. Okay, 2 websites to highlight. The first one is called CDAC, or Socioeconomic Data and Application Center. This is a NASA data portal, and here it's currently hosting daily 8-hour maximum and annual ozone concentrations for the continental US, and daily and annual PM concentrations for the continental US for 17-year time period. If you want to study globally, you can go to Randall Martin's website. At Washington University, they offer quite a few, global data sets in terms for PM 2.5, surface NO2, and many others. These are already converted to ground level mass concentrations. Okay, so you don't have to deal with the raw satellite data. Now, speaking of emerging capabilities, I want to highlight 3 satellite missions. The first is TEMPO, or tropospheric emissions monitoring of pollution. It'll be launched into a geostationary orbit over North America. As you can see in this table, TEMPO will be able to measure many atmospheric components at a fairly high spatial resolution hourly, from from sunrise to sunset. I just want to highlight one parameter here. I think the ability to estimate boundary layer ozone abundance will be very helpful for air pollution epidemiology. TEMPO is part of an international geo constellation, which will provide similar capabilities in the Northern Hemisphere. As you will hear in session 3 of this workshop, GEMS is initiated by the National Institute of Environmental Research of Korea, and it covers most of Asia. Now, GEMS has already launched in February 2020. And you will learn more about its capabilities and data products, like I said, in session 3 of this workshop. The next mission I want to highlight is MAIA, or multi-angle imager for aerosols. MAIA aimed at relating exposure to different types of particulate matter and a variety of health effects, including birth outcomes, cardiovascular and respiratory disease, and premature death. This is the first time NASA has partnered with the health community and epidemiologists from the beginning. From satellite design to implementation, to data production and application. The entire pipeline has the participation of the health, the representatives of the health community. And Maya will directly provide ground level PM mass and speciation concentrations. So it will first generate aerosol optical properties at 1 kilometer resolution. These and other auxiliary data will be used to estimate ground level PM in a Bayesian downscaler type of modeling system. And after that, a data fusion model will be used to combine the satellite PM data with calibrated air quality model simulations to produce a full coverage data layer. And the Maya PM data will be available only over a select set of megacities around the world. We call them the primary target areas and the secondary target areas. Okay, now before I close, I want to point out that this field is very, very young. I did a very quick Web of Science search using 3 combinations of search terms in the topic. So if I search PM 2.5 and mortality, I got over 6,000 papers since 1994. For the same period, if I add satellite as a keyword, the search returns only 472 articles. If I'm more specific and then I add AOD into the search term, I got 149. That's a tiny fraction of all the air pollution health effects research reports. The fraction of satellite applications is increasing slowly. If we only include papers published after 2018, I got a total of 3,500, of which 336 include satellite as a keyword. 93 include AOD as a keyword. So finally, some food for thought. There are still many challenges and opportunities in this space, and that's why we have this series of well-attended presentations. The challenges include, communication barriers between data producers and users. We don't normally walk in the same circles. Many satellite products need translation for health applications, and the data structure can be more sort of user-friendly. Currently, almost all satellite data are packaged in binary, non-human readable formats, right? You have to have a pretty significant coding skills in order to unpack them and use them. And in terms of opportunities, there's still an enormous demand for continued interactions between the health researchers and the representatives of the remote sensing community. And there's a need to integrate across different air quality monitoring technology platforms. Here, I mean satellites, gold standard measurements, model simulations, and the emerging low-cost sensor, crowdsourced information. And finally, scientifically, I think a very important issue to be addressed fully is the characterization of the impact of exposure error on the health effect estimates. We haven't done a whole lot in this space yet. So with that, I thank you for your attention.
Thank you so much, Yang. That really covered a lot of exciting ground that I think we can come back to in the Q&A at the end of the panel to go into. And I'll hand it back to Jeff to introduce our next speaker.
Okay, thank you, Tracey, and thank you, Yang. That's a great stage setting presentation there. So the next speaker is Dr. Qian Di, and he's an associate professor at the Venke School of Public Health at Tsinghua University. As you can see in his bio, among other things, he's been pushing the limit in developing exposure relevant information using satellite data. I think he represents a great complement from what we just heard from Yang. So go ahead, Chang, the floor is yours.
Hi, hello everyone. Welcome. It's my pleasure to give a talk here. let me show my slide and I think I should press this button. Oh, can you see my screen?
Yes.
Okay, good. Okay, hello everyone. This is Chendi from Tsinghua University, School of Public Health, and our school has just been founded about 2 years ago. So me and our school is really looking for collaboration with HEI and other speakers as well as all the audience here. So the title for today is about application of air quality modeling for epidemiological study in data-rich areas. So just to follow Yang Liu's talk, I will talk about my own experience about air pollution modeling, and more broadly, I will share my own thinking on air pollution modeling and try to come up with a paradigm. And for all the other my counterparts to think about. So I like to start my slide with some of the previous models. So Dr. Yang Liu's work is really comprehensive, which makes my talk relatively easy. So I only have to very generally skip to cover them very generally. So how to estimate air pollution modeling? Basically, there are many ways, and we can categorize them into different fields. For example, we can use aerosol optical depth as a main predictor to estimate PM2.5. So this is the first predictor we can leverage. The second approach mostly use the land use regression, such as road density and land use coverage and some other variables. So the third approach, you use chemical transport model. That is a computer simulation software which use emission inventory and use some 3D modeling and simulate the transportation and dispersion of the chemical compounds, and also take the chemical reactions into consideration and simulate the reaction and the formation of PM2.5 as well as its deposition. So basically, there are many approaches. So let's take them one by one. First is chemical transport model. I just list GeoChem here, but basically there are many other chemical transport models available. GeoChem is maybe the most user-friendly one, and some other sophisticated models include CMAC and other models. So chemical transport model is able to give simulation on PM2.5 as well as its chemical profiles, such as sulfate, nitrate, vinyl carbon, organic carbon, etc. And with quite good temporal resolution, and the simulation could be as high as hourly level. But the spatial resolution is not good. So the GeoChem simulation I used, its spatial resolution is about 50 kilometers, which is fine, but not enough for follow-up epidemiological analysis. So this is a chemical transport model. It's computational intensive. It requires a lot of coding, debugging, and also a lot of computation capacity. But this the strength is that it offers chemical profile as well as vertical profile. As Dr. Yang Liu said, aerosol optical depth is a quantum measurement of aerosol. It is an integral of all the aerosol concentration in the atmospheric column. So the surface level PM2.5, the surface level aerosol is very different from aerosol optical depth. So we need to do some calibration. And the GeoScam vertical profile is a very important scaling factor for us to calibrate ALD. So most people in this field, including some of the influential ones, like one Dankner, has leveraged vertical profile from GeoScam to do the calibration. So basically, to put it in a simple way, we have ALD, which is a column measurement of aerosol of the aerosol, and we have the vertical profile from chemical transport model, and we can do a very simple scaling and get a surface level PM 2.5. This is an oversimplified version of model, just to let audience to understand the methodology here. But basically, the relationship between ALD and the ground level PM 2.5, as well as the vertical profile, is nonlinear, and it's far from just a times a scaling factor. Very different from that. In addition to chemical transport model, people can use land use variables to do modeling. In my previous team, Dr. Itai Konok used the mixed effect model and LD with land use variable to estimate PM 2.5 in the study area. So the land use variable here is the main predictor to downscale to a finer spatial resolution. But the net use variable does have its own limitation, because net use variable, it's high in spatial resolution, but the temporal resolution is not good, and it cannot capture the day-to-day variation in the fluctuation of air pollution levels. So in addition to land use regression, land use terms, we can put a methodological variable to give the model some temporal variation. So methodological variables, such as some of the data assimilation sources, provide very good and easy to use methodological estimation, which is at either daily level or hourly level. Using those methodological fields, which they can give the model some of the temporal fluctuation, and this is a good complementary to land use regression. So I used that approach before as in one of my early work to combine land use terms with methodological variables to downscale GeoScam to a finer spatial resolution. So the methodological variable here is the temporal driver, and the land use terms here is the spatial driver. And by integrating them together, we got the chemical composition estimation of PM 2.5 at a reasonable time and the spatial resolution. So in addition to above mentioned variables, there are some other variables from satellite sensors which are also informative to modeling. For example, here is one variable I'd like to mention is absorbing aerosol index, so which is related to the chemical composition of PM. So PM is a chemical mixture, so it has different. So it is a combination of different chemical species, like sulfate, which is white color, and the soot or black carbon, which has dark color. So absorbing aerosol index reflect those chemical compositions, and this is related to the aerosol optical depth, because for the same amount of aerosol concentration, sulfate and black carbon certainly leads to different aerosol optical depth. And absorbing aerosol index is able to capture that. So certainly this variable is informative to the modeling work, and it is worth adding it into the modeling. In addition to that, we do have some other variables which are really also informative, such as surface reflectance. Um, because of the algorithm to derive ALD from satellite, if the background is very bright, such as desert or snow with snow coverage, in that situation, if the background is very bright, so the algorithm to estimate ALD is not as reliable, and it's prone to errors. So surface reflectance is able to capture that and to take that into consideration, because the surface reflectance is closely associated with the signal to noise ratio of ALD data. And for the same reason, NDVI, which is a proxy for vegetation coverage, is also informative. In addition to that, vegetation, forest is also a source of organic carbon. For example, in the southeast United States, forest there emits organic carbon, which is a precursor of PM. So adding vegetation coverage or NDVI into the model is able to capture that source of PM 2.5. And yes, we can also add meteorological fields into the model as a possible predictor. Yes, so in this section, I mentioned a lot of variables. As you can tell, those approaches, those variables do have its own limitations and weakness. And they are using one variable is not able to capture the whole picture of the formation deposition of PM, because the formation deposition of PM in the atmosphere is quite complex. It's a highly non-linear process. One or a few variables is only capture or partially capture the overall picture. If you put more variables into the model, you will be able to have a more comprehensive understanding of the entire picture. And if you add more variables into the model, you still need a good algorithm to simulate, to better recover the nonlinear relationship between the variables and capture the interactions between variables. And the neural network is one of the candidate algorithms that is able to undertake that task. So for the model training part, for some of my previous works, I used the neural network as a training algorithm. So basically, neural network is able to take multiple variables into the model and do the model training. And the input variables include, but not limited to, geochem output, geochem simulation of PM 2.5, the vertical profile of chemical transport model, aerosol optical depth, and the absorbing aerosol index, that use terms, meteorological fields, surface reflectance, and some other additional variables. And you put them into a neural network or other machine learning algorithms and conducted tenfold cross-validation, because this step is very important to avoid overfitting. If you do not do this task, the R square you obtained from the machine learning algorithm is inflated. I'd like to mention a little bit about why we need neural network. This is because the chemical reactions, the photochemical reactions in the atmosphere is highly nonlinear, and our current knowledge about them is very limited. We do not fully understand what's going on in the atmosphere, and some of the reaction parameters is not quite accurate. So instead of analyzing, trying to exploring the mechanism, we use a data-driven approach. We are trying to feed a massive amount of data into the neural network and use that neural network to decide how to simulate, how to recover this complex relationship. And this is the basic framework for neural network-based modeling. But the drawback is that we do not fully understand what's going on inside the neural network. For example, we often wish to answer which variable or which variables are most informative to PM2.5 modeling. Unfortunately, neural network is not a good algorithm to answer that question. This is also mainly the challenges we are facing. For example, driverless vehicles. We don't know what's going on. How the artificial intelligence make that decision. This is also the same also holds for here. Yeah, neural network also boost model performance, but the price we are going to pay here is that we do not quite understand the black box, what's going on inside the black box. Okay, setting the mechanism aside, setting the putting the drawback of neural network aside, just speaking of the model performance, the model performance is satisfying. So you can tell for the whole study area, the R square, I mean the correlation between predicted PM2.5 and monitored PM2.5 is quite high. Although there is a slight drop at the end of the study period. And the bias and the slope, so I take a linear regression between predicted PM2.5 and monitored PM2.5, and calculate the intercept and slope, which this is a way to access model performance. So slope is equal to 1 means there's no underestimation or overestimation. The bias is almost 0, which also indicates the good model performance. And by region, most epidemiological studies were conducted in the northeastern United States, and for that sub-location, for that sub-region, the model performance, you can tell, is also satisfying. So basically, from the correlation between monitored PM and predicted PM, the model is doing a decent job, and which allow epidemiologists to leverage this data set to access exposure with high accuracy. So this is some of the early work I will mention about my recent improvement on this work. Okay, so this is a correlation by monitoring site. I just interpolated R square at each monitoring site to the neighboring areas. You can tell the blue color stands for low correlation, and the orange color stands for high correlation. And the Middle East, the mountain regions have relatively lower model performance, which is not ideal, but considering less people living there and fewer cohorts from this study area, I think this is fine. This is fine.
Hi, Chen.
Okay, so
I think you have about 3 minutes left.
Okay,
And, I know
sure.
you have some great things to say about ozone and all
So
new directions and challenges. So try to
okay.
get things in the end if you can, please.
Okay, so using the same methodology, we can use that to model ozone, and with slightly different predictors. And for example, we should take the troposphere intrusion into consideration and all other secondary pollutant as possible predictors. So those are other predictors we can leverage. But as Yang Liu said, the basic methodology also applies for ozone modeling. Okay, for ozone modeling, we also put multiple variables into the regression model, into the neural network, and got satisfying model performance. And in terms of application, we can merge the air pollution modeling, air pollution estimation from the satellite model with Medicare with Medicare participants based on their residential areas, and conducted a survival analysis, which allow us to estimate the hazard ratio of air pollution, and especially when air pollution is at a low concentration. And what we find is very interesting. Even below the US standard, air pollution PM still is associated with elevated mortality. And even the previous WHO standard was not stringent enough. That is why the last year WHO updated its PM recommended level. And we also find marginalized groups such as African Americans and people with low socioeconomic status is very vulnerable to PM. And this is 2 minutes. So, yeah, this is a picture from very spicy food from my hometown, which is hot pot. And hot pot is a combination of different ingredients you combine different ingredients into the spicy sauce and create something very delicious. This is a good analogy what we are facing in air pollution modeling. So we put different ingredients into the model and the neural network or other algorithms and get a PM estimation. So following this paradigm, we can use this analogy to further improve our model. We can add more ingredients into our model, like road density and lead coverage, and CMAC output into the model. We can also choose better spicy sauce to use better spicy sauce, for example, an ensemble of several machine learners, and got improved model performance. So this is my second to last slide. This is my recent work, but this takes 2 years to do data cleaning and model training, and got modest improvement on model performance. So maybe this is a diminishing return. And similarly, diminishing return is also observed in machine learning. So for my last slide, I'd like to share some of my thoughts. First, as Yang Liu and my talks have demonstrated that air pollution modeling is like a hot pot. So we add different ingredients into the hot pot and add in some spicy sauce. And our ways to further improve the model is to add in more ingredients and change different sources. But some of the questions I wish to ask is that some ingredients certainly are more important than others. But if you put some numbers of ingredients into hot pot, you could have a decent hot pot. More predictors certainly helps, but marginal returns decreases. So I like to end up my slide here. At what point we should stop? So this is my acknowledgement, and I do and I like to to show my gratitude to my former doctor advisor and my teammates here in Tsinghua, and my team is also hiring research assistant and postdoctors. So thank you. I hope this analogy helps you to understand this field and to take questions in your Q&A session. Sorry, I think I running out of 1 or 2 minutes. Thank you. That's all my talk.
Yeah, that's very much appreciated. Thank you very much. You're making me hungry for more, for sure. We'll move on. I think there's going to be lots of good questions that you've sparked at the end. I'll turn it over to Tracey.
Yeah, thank you, Chen, and thanks, Jeff. And for our third and final speaker before we start the panel discussion, it's really an honor to have Anna Prados, who is a senior research scientist at Battelle, joining us. And Anna actually really is the force and the vision behind the entire RSET training program that we've heard mentioned quite a few times already in this panel. And so I think Anna will tell us more about RSET, but and her bio is also in the chat. So thank you, Anna.
Okay, I'm going to share my screen now. Okay, how does that look?
Looks great.
Okay, so I'm going to shift gears a little bit and talk about capacity development opportunities for improving the use of satellite data for health applications and also for communications. And I'd like to acknowledge my co-authors, Brian Duncan and Kevin Cromar, who are also part of HAQAST as am I. So I worked at NASA for 14 years and led the RSET program, the Applied Remote Sensing Training Program, for 12 years, and have worked in air quality remote sensing for about 20 years. So I'm happy to be sharing my thoughts on capacity development. And you know, I thought I'd start with, you know, so I'm going to cover kind of two main things. One is some of the current challenges in use of satellite data for health applications, but also how capacity development can help overcome some of these challenges. And I'm going to be focusing on challenges and barriers based mostly as they relate for the decision makers. So, you know, and I'm defining decision makers as the forecasters or people in the regulatory community, epidemiologists, folks in the health field. So those are the decision makers and the stakeholders I'm referring to when I talk about, you know, throughout my presentation. So, you know, starting with kind of at a high level, some of the current challenges that I saw in all the years I worked, you know, at NASA, you know, building a workforce that routinely uses satellite data. You know, there are a number of challenges. Some of them have been talked about before. Many of them are really institutional and organizational, such as, you know, the skills that are needed to be able to work with the satellite data, institutions having the budget needed to work with data sets that I'm familiar with and that are somewhat challenging to work with. And also just a general lack of awareness. I think we've made a lot of progress in increasing awareness, but we still have a ways to go. So still some challenges in building this workforce. And then there are challenges related to the data itself. And I'll talk a little bit more about that. You know, the data have been proven very useful for many health applications, but as Yang mentioned earlier, and I think it was mentioned in the previous talk as well, it's not suitable for some types of air quality management tasks, such as neighborhood level monitoring. So we just need to be aware of those limitations. So some of the barriers that are specific to health applications and to remote sensing data for health applications, relate to the access to the data and to the nature of the data itself, right? The spatial and temporal resolution has improved somewhat, and it continues to improve, but there's still some limitations. People sometimes report having trouble finding the data they need, issues with accuracy in the data, and more than anything, I would say, if I had to pick one, I would say working with the column measurements. As Yang said, people want, at least in the decision-making world and also in academia, people need surface concentrations. And people also need confidence, in that the data is going to be around, right? So if an organization is going to invest in satellite remote sensing, and there's an instrument that's only has 2 years life, it's going to be gone in 2 years, then they're not going to want to invest, right? They like to know that data is going to be around for a while. And also, if ground truthing isn't available, they're not going to invest in data that hasn't been ground truthed and that has been assessed. So those are some of the issues related to confidence. Knowledge gaps are various. Understanding the data strengths and the limitations, understanding how the data can be used for decision making and cannot be used, right? That's just as important. And also how to construct the analysis and interpret the results of the satellite data that both of the satellite data products. And then on the technical side, particularly, depending on where you are in the world, there could be issues with capacity to download the large data files, computational capacity, etc. So those are important as well. So, when I was leading the RSET program, we did a lot of work surveying the participants of the training program and collected a lot of very interesting data that we used to manage and to really design the program. And these are the results of survey data we collected from the stakeholders that attended the air quality trainings. And we asked them the question, do you think, are these, as listed here to the left, are these a barrier to you and to what degree, right? Is it a slight barrier, a moderate barrier, or a major barrier, which is what's shown in red? And we selected these categories and found that, for the majority of the users, it was it was a slight to a major barrier. And actually, in some cases, close to half of our attendees found things like spatial vertical data resolution, which tends to be at the top, a moderate to major barrier to their ability to use the satellite data. Accuracy is an interesting one. Data accuracy is important to some users. It's not as important for others. In many countries, we found that people were willing to sacrifice accuracy as long as it had the needed spatial resolution. So it really depends on the user. So that's why it's important to collect the information and to understand what it means and how it varies regionally and by the type of user. So we have published some of this data, published some of it recently, actually last year, specifically for the Spanish-speaking countries that we work with a lot in our set, so you can access the more information there and some of these barriers. So, two ways that I've encountered in my professional life on addressing some of these challenges through capacity development. One is through the professional training that is really often necessary for the decision makers, but is, although not necessarily sufficient, right? So again, necessary, but not sufficient. You need other things too, but training is still very important. But you can also build capacity through projects such as, we've seen it from the previous talks, where our remote sensing scientists can work directly with the decision makers to deliver tailored data products or analysis or services to meet their needs, or a combination of the two. And I'm going to start by talking a little bit about the training side of things. So from my experience at NASA and many other agencies that also provide training, of course, online training took off about maybe 7 or 8 years ago. That's there's a lot of resources for online training. Some in person are a little less because it's less costly. It's more costly. And there's also hybrid approaches. The training can be on demand or it can be live. And, ideally, agencies provide training at multiple levels, because some people are at the basic level, but some users are pretty advanced, and they just, they want to get right to the more advanced topics and applications. We did multi-language training at RSET, and the program continues to do so. Very important, if possible, to reach users in their native language. I mean, I think that's kind of obvious, but there's actually a real lack of access to multi-language training. Most of it is in English, and that's not going to work for everybody. So, and also tailoring the trainings to the audience, right? Academics versus decision makers versus other types of users. So in terms of the training content development, to learn about remote sensing, health applications, define the user needs in order to design these trainings. Working regionally tends to be better. I mean, as we all know intuitively, air quality challenges vary by region. Involving the end users in the actual design of a training is very important as well. They know their region, they know, they know their landscape. Talking about what are the relevant data. A lot of users talk about how they don't know how to find the data they need, because there's like millions of data sources, not just from NASA, but other space agencies that are, thankfully, they're freely available, but it also creates a little bit of a issue when there's so many data sets to choose from. So guiding users through that, and also guiding them through the various resources for accessing the data and analyzing it, whether they're web-based, desktop, or through scripting. And then, in terms of working with the decision makers through training, yes, the data is there, but now what do I do with it, right? So it needs to be taught in a training environment. It needs to be taught in a way that it is, so that it's in the context of what they do, what the decision makers do. Whether they're monitoring, or they're involved with regulation, or they're involved with communications. It needs to be explained how the data can be applied to these specific applications. Hands-on exercises, very, very important. We did a lot of that through the RSET program. They're all freely available through the website going back several years. And that website was shared earlier. And then, I think evaluation is important for any program, and there's, and it's also true for training and skill and building skills and professional development, and collecting the data from the users is important. Are they benefiting from the training? How are they benefiting, and how can the program be improved? All this information is important and needs to be collected, I believe, on an ongoing basis to make a training program effective. So I think I have about maybe 7 or 8 minutes. I'll talk I'll switch gears. So training is one way to build capacity. So then I'm going to talk about the NASA program that I'm involved with, which is a HAQAST project. So it's called Integrating NASA Resources into the, sorry, I'm having trouble here reading my slides actually. 1 second. Okay, integrating, I can't read the full title, but integrating the NASA resources into the operating procedures of air quality agencies in low and moderate income countries is the name of our project. So what we're doing in our project is working with cities across the world to help them build a more comprehensive approach to air quality management. So they might already have tools and do have tools in their toolbox they're using to manage air quality. So how can we work with them to add a variety of NASA resources? And these do include, in our project currently include the forecast side of things, which is what's on the left. So the center we have, okay, that's the decision maker, that's your stakeholder, that's your type of air quality management activity they're involved with. And then NASA has an air quality forecast system that I'll talk about it in a second. And there has been an ongoing NASA effort for a number of years now to work with cities to provide tailored forecasts of air pollutants. And these tailored forecasts are accomplished by combining NASA's global air quality forecasting system with ground-based observations, and then through machine learning providing tailored forecasts for these cities. So we're working with cities right now to make these available and also making resources available to them related to the satellite data. And we also have partners that we're working with on low-cost sensor options. So our team is led by Brian Duncan at NASA. We also have a number of scientists from NASA's Global Modeling and Assimilation Office, also known as the GMAO. Our partner, Kevin Cromer at New York University. And then we have partners from UNICEF as well as Clarity Movement. So I'd like to go back for a couple of minutes on the forecasting side, because this is really a unique NASA capability that I think maybe people aren't aware of. And so we, NASA's been really put quite a bit of effort into this over the last several years. So the NASA, it's called the NASA GEOS Composition Forecast System, or GEOS-CF. And so it has two components. It has it's constrained by meteorology from the GEOS-FP system itself. And then, which I'm not going to talk about, and also GeoSchem, which you have heard about. That's where the chemistry part comes from. And you can get a daily forecast globally, for a number of species, including ozone, nitrogen dioxide, and fine particulate matter. Also, not mentioned here are carbon monoxide and sulfur dioxide. And the nice feature here is that you can select specific cities. You can go to the website. I think I share I think I'm sharing the website is somewhere in my presentation, and you can actually select cities and get your forecast for your city. So multi-step approach to working with cities to build our capacity to use satellite remote sensing for air quality. We've had initial conversations with a number of cities already in Africa and in Latin America. We're still working on identifying which are going to be the final cities, but work is ongoing with a number of them already. We're providing resources related to training, etc. Also developing illustrative case studies and exploring messaging opportunities. We're kind of working on all of them concurrently right now. I'm going to talk in a couple minutes just about, I have like just 3 slides left. Examples of resources we're making available to cities that you can access as well. They're there already. Worldview is one of several NASA portals for access to data and visualization of the data. These are data products kind of ready to go. You don't have to analyze the data. You can download plots, etc. NASA Gather has an air quality webpage with lots of resources. And then, okay, here's the air quality forecast webpage, number 3. Number 4 is the RSIT program that we've talked about already. And then there's HAQAST, the Health and Air Quality Applied Sciences theme, which also has tons of resources. And here's a link to a YouTube video that describes all of these. And we've also worked with these stakeholders. We're also currently developing case studies for the cities we're working with, so that we can better. This enables us to share the capabilities that NASA has to offer. And the idea here is that by using these in conjunction, you're going to be able to do a better job of understanding, forecasting, and generally for air quality management. And here's an example of one we put together and recently presented to stakeholders in Kigali, Rwanda. You got the satellite side of things on, to the left, then the air quality forecast are the second and third panels. And the forecast, you can also get the data, this is the third panel here is a time series, in the x-axis, and then the y-axis is actually pressure levels. So there's all kinds of different ways you can plot the data. And the last part of our project is the messaging and the communication side of things, very important. So we're working with our colleagues at New York University. Kevin Cromer is doing this work. So air quality indices have been around for a while. You know, they're a much better way to communicate to the public the health risks of air quality, as opposed to throwing around, you know, concentrations, which we scientists like to work with. So these indices can be multi-pollutant, they could be single pollutant. The indices we're working with are multi-pollutant. It's called the HAQI, or Health and Air Quality Index, which was developed by at New York University. They've done work with Mexico already in developing this index. The input to the, you know, it uses PM2.5, ozone, and NO2, so it's multi-pollutant, which in this information can come either from local data from a monitor, or it can come from a model, you know, a model, and Kevin's used both. And the model, of course, many of the models have satellite data, are constrained by satellite data. So satellite data does have an important role to play in these indices. And we are currently working with Latin America and Africa, African cities, to evaluate the Health and Air Quality Index for risk communication as part of our project. And I think that is my last slide. And here's my contact info.
Thank you so much, Anna. There's so many threads that connect all of these different talks. I'm really excited to get into these topics in the discussion. So I'll hand it back to Jeff to kick us off.
Yes, thanks everybody. Thanks for the presentations. I think they really line up nicely for setting the stage. And there's been a number of questions that people have submitted. Some have been answered. One of the topic areas where I saw a couple different people ask questions was around the growing amount of low-cost sensor data sets that are out there. Conceptually, maybe there's two ways that these sensors could be complementary to, you know, estimating exposures. One could be input into the hot pot, so a model predictor, but we know with considerably more measurement error. Another way could be that maybe satellites could help validate some of these sensor data. So the sensor data themselves could be corrected. Are there any thoughts that you may have in this? Maybe Chian could go first, because he just sort of talked a bit about the hot pot concept in the diminishing returns. Are these diminishing returns? Well, I see Yang, you've got your camera on too. So comments on the low cost sensor data.
I guess I'll let Chen to kick us off.
Yeah, Chen, you have any thoughts on that? But Yang, if you
Oh,
want.
yes, I do. But I don't know how to turn my camera, but I guess this is okay because my microphone is on. So we do have a project here using low-cost data to do some modeling work. So we ask some students, we recruit about 100 students in Tsinghua and ask them to put a monitor with them for 1 week. And that monitor is able to measure personal level PM2.5 for 7 days, 24 hours. And we are leveraging that data to come up with a personal level estimation, combining with the monitor data from the nearest fixed stations. So I think certainly my experience on this project is that certain low-cost data is certainly helpful, but the problem is the uncertainty is quite unstable. It is quite unstable, you know. Some monitors, they are very accurate and they can monitor PM with quite stable accuracy. But for some monitors, you just cannot guess their uncertainty. So my thoughts is that we really require some new methods like Kalman filter and data assimilation approach for us to leverage how that data. And in the future, there will be more such data coming. Think about the IoT, Internet of Things. You will be able to put millions of low-cost sensors on different objects, which will be able to produce PM measurements in a continuous manner. So we need some breakthrough in statistics which can leverage that data. some algorithm like Kalman filter would be such candidate methods. That's in my short answer.
Oh, thanks. I see Anna has her hand up, but Yang, did you want to follow up first and then Anna?
Yeah, I mean, that's an interesting idea, right? But I think realistically right now, because most of the satellite missions don't directly measure PM, for example, there is a conversion in order to use the satellite data. If that conversion does not involve sensor data, we can make a comparison. But more realistically, and maybe more valuable option would be to use satellite data to guide the siting strategy or deployment strategy of sensor data. Because satellite does have a more kind of a consistent texture, unlike sensor, which is more organic. Sometimes there's dead weight in the network. You can deploy 2,000 sensors without representing the spatial characteristics that you want to see. So that's a real concern. So I think that might be kind of more of a near-term objective.
Yeah, that's very complimentary that way. That's a good thought. Anna, you wanted to add to this?
Yeah, I mean, so low-cost sensors are being used across the US for a number of applications. I mean, I guess maybe this is a little outside of the satellite side of things, but I did want to comment on the fact that, you know, the EPA funds a lot of projects in the use of low-cost sensors. It's being used for environmental justice applications. And I think Yang may have just mentioned this, but they have an important role to play in the siting of ground-based monitors, right? Because citizens can use them and are using them, and yes, they have accuracy issues, but they're catching issues that are being missed and are then that's leading to the placement of monitors, continuous monitoring that could lead to the to more focused regional satellite studies, right? Where these problems are being identified that hadn't been identified previously. So I think they're important despite some of their limitations.
Yeah, thanks for your input there, Tracey.
Yeah, thanks everyone. The next question was posed by Robert earlier in the session, but I think it actually weaves through many of your presentations, asking about whether the satellite data are reliable over Africa because there are very few in situ data to support validation. And I'm going to give Anna the floor to begin since she explicitly addressed data needs for Africa, but I'd like to also hear from Chien, who with your map on agreement in data poor areas, I think is very relevant to this issue as well. And I know Yang has worked on a lot of global health topics too. So Anna, what do you think about applying satellite data where you're lacking in situ data for validation?
Yeah, I mean, so I think in Africa as well as probably some other areas, I think when we're talking about larger regional scale pollution and transport of air pollution, like from smoke, I think it is being used in that way and it has been proven to be useful. I think if you're going to use it more for city scale, monitoring or smaller scale, and you don't have the ground-based data, then it can be more problematic because you just don't know, how good your data is. But we're using it with our partners in Africa for more of the regional scale type processes. So those are my thoughts. Yeah.
But Chien, do you have any thoughts on that from your analysis that you presented over the US?
It really depends on the epidemiological study we will do with the African data. So if we do some cohort study, really relies on spatial contrast of PM 2.5. In that study setting, I think that will be an issue, especially if all the cohorts are living in a very small study area. and that means they have a relatively small spatial contrast. That will be issue. But if people are conducting some time series and time series data, I think PM2.5, the PM2.5 model usually does a decent job to capture the day-to-day variation. So I think the time series data leveraging PM2.5 estimation from satellite will do a decent job. So it really depends on the epidemiological study people are doing. But the principle is that you'd better to have a study population with relatively large exposure contrast, and that will give enough signal to noise ratio for your analysis to detect.
Thank you. Yang, do you want to contribute, or should we go on to the next question?
I mean, I generally agree with Chen's idea. It depends on the study design of the health effects research. So the answer is maybe.
Okay. Jeff, you want to pitch the next one?
Yeah, many questions here. I'm trying to compile some together, but one of them that I think is important for us to get a better appreciation for is just sort of the error or uncertainty estimates that we see from the satellite products, whether it be the sort of direct retrievals or from the more composite estimates. We saw tables with R-squares and things like that in some of these presentations here. What can any of the panelists say about the reliability of these uncertainty estimates and maybe their applicability in health research questions or other? Any thoughts on new metrics that might be more useful or directions to go there? If not, I have a sort of more follow-up nuance to that question.
So I'd like to give my thoughts on this question. So all models are wrong, but some models are useful, of course. So R square is really a tricky matrix. So R square quantifies how wrong we are when we do the modeling, but R square only captures the overall agreement. Some other metrics like slope, intercept, and MSE certainly helps, but they only capture the correlation, captures the distance between the high dimension space in a partial way. So I think we certainly need more metrics, but those metrics may be hard for people to understand. So considering the difficulty and the how people can understand the indicator, maybe R square is a good enough choice. So which is not perfect, but which is acceptable and good enough for most users. And for the person who asked this question, I suggest to use R square to just look at the study region he or she is focusing on, and also take a look at the study period he or she is focused on, and get R square that is mostly associated with the study design. Yeah.
Any further comments on that question? I just want to extend it a little bit because Alan Krupnik asked a good question about application early on in the question and answer about whether or not tools could be available where users could do their own more local calibrations in a certain time or domain. We know, of course, that these outputs are often now calibrated and go into the models with surface data calibrating everything to be reliable. But they do it for the whole domain of development. So is it possible to have tools where a user might say, I want to actually take this product and further refine it for my own temporal or spatial domain? Maybe that's something that HAQAST can tackle.
Jeff, I think that's a great question and really something for HAQAST to think about. I don't believe there is a tool right now, kind of a plug and play type of application that you can just use. And I don't have a straight answer to that, but I think that the question's definitely legitimate.
Yeah. I mean, if you see the R squares, they can look really good if you pick a large domain with a lot of variability versus a smaller area. And so this question of the domain for your application is really important.
Mm-hmm. Agree.
Thanks for your input. Tracey, do you have a question you've sifted through you want to put to the panel?
Yes, I think another question that came up was the role of different organizations involved in providing and explaining this. And Alan mentioned the role of the EPA and the Clean Air Act, because so far there's been a lot going on around NASA trying to engage users. And now with this panel and this seminar series from HEI, the health community engaging, I guess, what do you see as the role of the EPA? Maybe Anna, you can start that, because I know you've worked closely with EPA on a lot of this.
Yeah, the role of EPA in, can you hone in a little bit on the role of EPA?
I guess on connecting satellite data with air quality, because EPA currently oversees the state-of-the-art monitoring network in the United States, and they develop a lot of the modeling tools. Is satellite data appropriate for EPA to take on under the Clean Air Act?
So, they're already using it as for some, a lot of their regulatory models, right? So they use it to constrain emission inventories. Satellite data was very important in actually helping EPA realize they actually had an issue with their emissions inventories some years ago, because they were underestimating, I think it was NOx, they were underestimating, or I think overestimating. So they're really kind of on board to some degree, but the accuracy issues do limit it in their eyes, right? I don't think it's the data have the accuracy to be used for like exceptional event determinations and that kind of a thing. So I think however, as the data become more better spatially resolved, which they're going to, right, with template some of these missions, that could change. So right now, I don't see things changing very much until we get the new satellite data in. EPA is more involved than it used to be in the design of the satellite missions. That's key, right? Because there are decisions to be made when you're designing instruments on what bands you're going to use and what specifications that are going to be really important to agencies like EPA. So they need to be part of that conversation. But the data is not there really beyond, I think what they're doing right now because of the limitations.
Now, I recall, I don't know how many years ago, so I'm dating myself, when Ray Hoff was the critical reviewer for the AWMA and asked the question about how we reach the promised land. And it was someone in the context of, are satellite-based products ever going to be useful for determining attainment in different areas? I'm not sure if we're yet at the promised land in that area. Still an ongoing question. Another question that I noted, and maybe Yang wants to comment on this, it sort of maybe touches upon the diminishing returns, is that as these models ingest more and more ingredients into the hot pot, and then you look back, if you can, at what predictors are most important, often the satellite inputs aren't the most important predictors. And does that mean we should still say, well, drop the satellite out and now it's cut out of the game, or should they be forced in there? Like, what do you think about that as we put more and more predictors? And of course, we're living in this, maybe it's actually the metaverse. We're seeing satellites aren't the most important predictors.
Yeah, that question gets asked a lot in the latest round of article reviews, right? The reviewers want to know what's the most important predictor. I think there are several factors to consider. One, we are so used to performance metrics such as R-square, root mean square error, and these two dominant ones really don't do justice to the satellite contribution. Very often, the cross-validation is done at the monitoring locations. It doesn't really factor into the contribution that satellite makes to characterize the spatial patterns of pollution outside a monitoring network. And number two, satellite, at least in my own experience, satellite points out hotspot and unexpected hotspots far beyond the ground monitoring network, especially in situations such as wildfires and dust storms. And yet that contribution cannot be seen in root mean square error estimates or R-squared estimates. Therefore, I often argue that we have to look beyond these population level metrics and really look at the prediction maps and see if that makes sense. What's missing from the non-satellite driven models, and very often we can clearly tell why we want satellite data, even though R-squared doesn't change. It doesn't change by 0.01. And in that case, I argue still, if the spatial contrast is very important to your study, even though it doesn't, AOD does not rank very high in your importance ranking, you should still keep it.
Yeah, I think that's really, really an important concept to remember. There's so many applications. Other thoughts on that? That's, one of the questions that came up that certainly is a curiosity to me is, just in terms of like the technology of satellites, how resolved, can they actually see? We know, of course, that the vertical profile is always going to be a limitation if you want to estimate surface measurements. And of course, depending whether it's nadir or angles, the resolution changes. But how resolved do you think satellites could get given current technologies? Anyone want to tackle that?
I can say a few words. Even just look at the standard product of Maya. The operational product has a resolution of 1 kilometer, but most of the channels are designed at 250 meter or 500 meter resolution. So in theory, we can quadruple the spatial resolution off the bat. That's how Maya came to place. Remember, we used to have the 10 kilometer resolution standard MODIS product, and then we have the 3 kilometer urban product. Without changing the sensor data at all, we now jump to 1 kilometer resolution Maya AOD, and the performance is just as good. So I think realistically speaking, we can get to the sub-kilometer scale without any issue. Now the question is, many epidemiologists would actually question the value of have hyper resolution exposure data in capturing the personal and the whole day exposure. We do, we kind of sit around all day, but we do go out to buy grocery, pick up kids. Our activity radius goes beyond a square kilometer very often. And do you really need a 250 meter product for PM? Maybe for black carbon, I see that, maybe even for NO2, but for ozone and PM, that's not even necessary.
Yes, I'm noting here Alan Krupnik, who asked a sort of similar question about whether or not 1 kilometer resolution is good enough for health research, is sort of posted in a bit of a disagreement to that. But that is sort of an important question, and it depends on, I guess, the health data you're working on, the population you're working with, the type of exposure you're interested in, and certainly certain sources and certain exposures are going to require finer resolution. I think we're drawing near close. Unfortunately, there's many more questions I'd like to bring forward. Some of them I think will be addressed in other sessions, so I do hope everybody will join again in some other sessions. But I'm going to turn it over to Tracey now for some closing observations, and then back to Allison. So Tracey, please go ahead.
Yeah, thank you to Jeff, and thank you to the panelists and the participants with the questions. This has been really an exciting session. And it's so wonderful that HEI is taking on this issue of satellite data for air quality and health applications. Because in the past 10 years, through the NASA applied science programs, there's been an effort from the NASA side to be bridging with user communities. And really through this discussion, it's the very first time that I've seen a large scale health-oriented organization, especially one as impactful as the Health Effects Institute, take this on in such a nuanced, thoughtful, and expansive way. And so today's session was really just phase one of this multi-part discussion series, but I think we've already hit on a number of really key issues. First is the diverse needs of the audience, that the study design, the community, the pollutant, the health effect, really all inform what are the appropriate sources of data and whether the resolution is appropriate, whether the characteristics of satellite data can support it, and how, in what way should it be combined with other data products. And I really loved the hot pot methodology. I'm a baker myself, so every time I talk about satellite-derived products, I use the baking metaphor, where we have different recipes and different ingredients. But I think that the different food genres all fit together to highlight how this is not just something, satellite data cannot just be plugged in lieu of ground-based measurements. They're not substitutable. The utilization, the effective utilization of satellite data requires multiple data products really coming from multiple disciplines. And as Yang noted, and Qian and Anna all hit on, this is a rapidly growing field. It's a young field. We're just beginning to sort of scratch the surface on how satellite data can be best applied to new problems. And I think the Maya mission is so exciting because it's the first NASA mission that's been led and designed with a focus on health applications. And as Yang mentioned, the resolution of Maya is going to be excellent. The trade-off is coverage. Many of the data products we've been mentioning so far offer global coverage every day. And this really expands the applications and communities who can use these data. As you start focusing on limited scales, it limits the area over which studies can be done, but opens up new opportunities. So I think as we move forward, really the question is finding the right toolbox, recipe, and audience to move this field forward. And with that, I'll hand it back to Allison to tee up what's coming next from the Health Effects Institute. Thank you all so much.
Yes, thank you so much, Tracey, for that overview of what we've learned so far and the questions to address in the future. And thank you to all the speakers for joining us today, and all the audience for your participation in the Q&A in the chat. So this was the first session of 4 in the workshop. So we hope to see many of you next week in the session on global applications of satellite-derived air quality data. In that session, we'll get into a lot of the questions on how satellite data are combined with other data sets, including ground monitors, and how those data are being used around the world. So I encourage you to join us there. If you haven't already completed the pre-workshop survey, we'd love to hear about the work you're doing or the work you want to do and are trying to learn the information you need to do that work successfully. We'd also like to invite you to the HEI annual conference. It's going to be held in person in Washington, DC at the end of June. And there's also an option to register for some of the sessions and join virtually. So we hope we'll see you there as well. Thank you for joining us and have a great rest of the day. Thank you.